Today we are going over lesson 2.6, rational function and asymptotes. So what is a rational function? A rational function takes the form of f of x equals n of x over d of x. Generally speaking, we have a number of x in the denominator to make this a rational function. Vertical asymptotes are what? They occur at, generally speaking, values of x where the domain is not including that x value. So there will become a line going up and down vertically, x equals a, an example for that value, where y goes to infinity or negative infinity as x approaches that value. So the graph will never cross that value. So just a quick picturesque look. Let's say for this little picture, x cannot equal 1, so we'll have a asymptote. What they mean is the graph might look like this at that point, where we're approaching infinity or negative infinity at that value. Okay. A horizontal asymptote is much similar to end behavior, right? The line y equals b if y goes to b as x goes to infinity or negative infinity, right? So that's kind of like our left-hand, right-hand end behavior. The graph may cross that line in the middle. However, if you look back at vertical asymptotes, the graph will never cross a vertical asymptote because, again, if x cannot equal 1 like we had in that graph, we can't cross that line. Right? Finding vertical asymptotes. What are we going to do to find these asymptotes? We are going to simplify the given function and then set the denominator equal to 0 and solve for x. Because remember, denominators equal 0 would mean dividing by 0, so we can't divide by 0. So whichever x value causes us to divide by 0 will be a value of x, which will have a vertical asymptote. Finding horizontal asymptotes. Now again, horizontal asymptotes is basically end behavior. We're simplifying f of x, where n is degree of n of x, and I'm going to switch that to d is a degree of denominator of x. Right? N for numerator, d for denominator is just going to keep us simpler. So what if the numerator is less than the denominator? If numerator's degree is smaller than the denominator wins per se, right? And then our y will go to 0, aka the x-axis, will be the horizontal asymptote. If n and denominator are equal, right? If they're equal degrees, right, they'll cancel each other out, the x values will, and then we'll be looking at what are our leading coefficients. So our asymptote becomes leading coefficient of the numerator's degree over leading coefficient of the denominator's degree. And then finally here at the bottom, if n is going to be larger than the denominator degree, right? So numerator degree is larger. That means we won't have an asymptote, right? No horizontal asymptote. Okay, so we'll see examples of these as we go on here. Starting off, we're going to match the equation with its graph, and we're going to state the vertical and horizontal asymptotes. Okay, so starting with 1, we've got f of x equals 1 over x minus 1. So starting off with vertical asymptote, right? Reminder, vertical asymptote is where the denominator equals 0. So it's kind of small, but we've got x minus 1 equals 0, plus 1 to both sides, and we're going to get x equals 1 is our vertical asymptote. Next, our horizontal asymptote is what is the degree of the numerator versus degree of the denominator. Simply put, we're comparing the leading piece of the top to the leading piece of the bottom. And we get 1 over x, which as x gets very large, we're going to get y equals 0. Using the degree comparison, the degree of the top is 0. The degree of the denominator is 1. Denominator wins, or denominator is greater than. So we'll have y equals 0 is our horizontal asymptote. And now we're looking for the graph that has these. Now looking, we got x equals 1 right here. That one has an x equals 1. It also has another asymptote over here, so that one's not going to be our number 1 graph. Moving to the right over here, we've got one that looks like it'll be our asymptote. But remember, this line is going to be our asymptote going left and right. And that clearly doesn't match. So it's not going to be that graph. Moving on to the bottom, we've got another one here with x equals 1. But our horizontal asymptote, again, would be this line here. And that doesn't seem to match. This side's over here. This side's up here. So it doesn't quite match. Right down here. And so it must be this last one. But let's double check here. We've got our up and down here, and then going across left to right. So those are our two asymptotes that matches. So this one's number 1. That is the 1 over x minus 1. Next equation, we've got 5x over x minus 1. So again, the same thing up top over x minus 1. X minus 1 equals 0. We got x equals 1 is our vertical asymptote, or our VA for short. Horizontal this time, we have 5x over x. So the x's cancel, and we get y equals 5 is our horizontal asymptote. Now that's how I like to do the asymptote, just comparing the leading coefficient degree piece of the numerator versus denominator, and then seeing what cancels. Right here, the x's would cancel. You can still memorize the degree rules, right? The degrees match the numerator and denominator, and equals d means 5 over 1, because of how much of each piece we have. So y equals 5, what we're looking at, coming back here, this top one's not going to work. It looks more like 3. Over here to the right, 1, 2, 3, 4, 5. Oh, here's our match. This one appears to be y equals 5. And so there's number 2. Next, we got 3x over absolute value of x minus 1. We won't see anything like that on a test or quiz, by the way. But set this equal to 0. X minus 1 equals 0. Again, x equals 1. Now, because of the absolute values, it throws our graph off a little bit. So we are comparing 3x over the absolute value of x. And that's a little goofy, because when x is negative, the bottom is positive, top is negative 3. Right? So negative 3 over positive 1. Right? So on our horizontal asymptote, because we already found our vertical here, right? Horizontal on the left is going to be negative 3. Right is going to be positive 1 over positive 3, which would be 3. So that's this graph that we're writing on right here. This is number 3, right? Our left side is minus 3, right side is plus 3. And again, we won't run into anything like this on quiz or test. Generally, our end behavior is going to be straightforward. That leaves us top one for number 4. We've got it matched, but let's still state our asymptotes. We're going to go down here. Why did that one have 2 asymptotes? Oh, this is why. X squared minus 1 equals 0, plus 1 to both sides. X squared equals 1. Square rooting, we get plus or minus. Sorry, only on the side of the number, we get x equals plus 1 minus 1. So that's why we have 2 vertical asymptotes. And our middle behavior is a little different. We'll talk about that in a moment. But then horizontally, 3x squared over x squared gives us 3 equal to y. And going back up, right, that makes sense that going left and right, we're approaching 3. Moving on, find the vertical and horizontal asymptotes, find holes in the graph, all stuff. I will talk about holes when they come up. Generally speaking, holes only happen when you simplify for this class. If we simplify, meaning say this equation on the right here is x over x included, so it's like 5x minus x cubed over x cubed minus 4x, right? Because we could take a 0, x out of both top and bottom, that would we would do that to simplify, but it would cause there to be holes when we graphed it, right? So anyway, we'll go over that again when we reach one. But vertical and horizontal. So VA, vertical asymptote, denominator equals 0. X squared minus 4 is 0. X squared equals plus 4 by adding 4 to each side. Square our root and add our plus or minus. X is plus 2 and minus 2, or plus or minus 2. So let's write that. And then checking our horizontal asymptote, I get y equals -1. Okay. Now, where did that come from, right? We've got negative x squared, positive x squared, our leading degrees. The x squareds cancel each other out, and we get -1. Next one, 3x over x cubed minus 4x squared minus 5x. Okay. So we've got an x in the numerator, and we've got an extra x in the denominator. So let's factor it out first. We've got x squared minus 4x minus 5, and then 3x in the numerator. This is what causes a hole, right? These x's are going to cancel out, but the domain of this equation, before we canceled that out, was x cannot equal 0, as well as x cannot equal, we got two values, we'll find in a second. But because the domain was part of x cannot equal 0, 0 doesn't come with, even though we canceled it out. So when 0 doesn't come with, that causes a hole, which will be at the point of 0, and then when we plug 0 into what's simplified, that will be our hole. So simplified form here, from what we just took out the x, if you plug 0 into that, we get 0, 0, minus 5. So this becomes 3 over minus 5, and that is -3/5. So 0, -3/5 would be our hole. Okay. Now, finding our vertical asymptote, getting to the actual problem here, right? It did say earlier that we needed to simplify before finding it. So that was part of the simplifying. If you simplify, we will find the hole. Vertical asymptote, we set the remaining x squared minus 4x minus 5 equal to 0 and solve. It's a quick factor. Again, numbers that multiply to equal -5 add to equal -4 are x minus 5, x plus 1. And then we set each of those equal to 0. I get x is 5. And then opposite of plus 1 is -1. So my asymptotes are x is -1 plus 5. Our horizontal ones are, we're looking at 3 over x squared. Right? X squared wins. The degree is 2 on the bottom, 0 on the top. This is going to be a y equals 0 asymptote. Next one, if you're getting the feel for it, pause the video and try to solve it on your own. Okay, in solving it, set the denominator equal to 0, x plus 1 equals 0, subtract 1 from each side, and we get x equals -1. So vertical asymptote, x is -1. Horizontal asymptote, I'm comparing the 3x cubed to the x in the denominator. 3x cubed is going to have a lot left over, right? This would be 3x squared. As you plug in large numbers, you will get that we will have no asymptote. We can say none, or the symbol is generally a small 0 with a slash through it, standing for null. There's none of them, null set. Next one, we've got x squared plus x minus 2 over x squared minus x minus 6. You do want to work to simplify just in case something does simplify out. So factoring the numerator, numbers that multiply to equal -2 add to equal 1 are going to be +2 minus 1. And then the denominator, right? Numbers multiply to equal -6 add to equal -1 are going to be -3 plus 2. And this canceling out is going to give us a hole. Right? We just had originally there x cannot equal -2, but now that we cancel it out, it's going to look graphically like x could equal -2. So to take care of that, we're going to plug -2 back into what's simplified. So we've got x minus 1 over x minus 3, plugging in -2. This is going to be the y value of our hole, because -2 is not in the domain of the original problem. Repeated it a couple times, but just trying to be consistent. So there's a hole that when we plug -2 in, we got 3/5, but x cannot equal -2, so that is our hole. And now doing the rest of the problem, right? Vertical asymptote of the simplified form, x minus 1 over x minus 3. and I get x minus 3 can equal 0, so x equals 3. And then comparing x over x, right, we get 1. So for horizontal asymptote, y equals 1 would be our general end behavior of the graph. Moving on. And again, if you feel like there's not a lot of time at the end of these slides, you can always press the pause button to buy yourself more time to say, fill in the last little bit of notes. Right? You can always pause the video and then write it down and then resume. Find the zeros of the rational function using a graphing utility. Okay. Now this is just to kind of show you where the zeros are coming from. So I'm going to graph this x squared minus 4 over x plus 3 on the TI here. So bringing it up and trying to fit it in this space. There we go. So again, we had x squared minus 4 over x plus 3. So note, it is a numerator, so I'm putting parentheses, x squared minus 4 parentheses, x minus 3. If you forgot the parentheses, I guarantee graph will look a bit different. We graph it. So where's our zeros? Looking at the graph, we can trace them. Again, you hit second trace button. We calculate the zeros, right? But looking at the graph, it appears to be minus 2 and plus 2. So that's what we're going to call it. We say x equals minus 2 and plus 2. Now, where did those come from? Right there, right? That came from setting the numerator of x equal to 0. Will give us x squared minus 4 is 0, and then x squared is 4, and so on. Right? That's where it came from. So that's just something to kind of keep in mind as we move closer to graphing these rational equations. That will be one step of our graphing. We've got a real-world problem. We've got, in a pilot project, a rural township was given recycling bins for separating and storing recyclable products. The cost in dollars for supplying bins to P% of the population is given as C equals 25,000 P over 100 minus P, given 0 less than or equal to P less than 100, right? Makes sense, percent would be between 0 and 100. And it says use a graphing utility to graph the cost of the function. So plugging it into our graph here, then we've got parentheses, 25,000, x in my equation divided by 100 minus x. Match, okay. And so then when we graph it, you'll notice we don't have enough graph space here. Don't see much, right? So we need to zoom out, and we can either zoom window, or you can make your window, right? So our minimum x value, we're going to go 0 to 100. We'll go 101 just so we can see the whole graph. Scale can be by how much we're moving when they have those tick marks. Going down, our minimum y value, we're going to go 0, and it's going to get pretty large here. We'll say we'll go to 500,000. And they can go by whatever, 50,000. So now when we graph it, we'll see a little bit more here. And there's the graph. Kind of looks exponential per se. And so we've got a graph. Check that off. Next, find the cost of giving bins to 15% of the population. Now we can trace and say x is 15, right? That's what we do. Otherwise, clearly you could just plug 15 into the equation in the numerator and denominator. But bring the calculator back out. I do trace 15. And I got 4,411.76. Now, if we're talking dollars, it doesn't make sense to round to the third decimal, so we're going to leave it at 2. 411.76. Sorry, 4,411.76. Okay. What about if we gave it to 50%? Right, again, same idea, we just got trace x equals 50. We're going to trace 50. And now it's quite a bit more, $25,000. And lastly, it says find the cost to give it to 90%, and then is it possible to give to 100%? So one more trace, 90, Again, why isn't it 0.9? Could be a smart question. And because it said percentage is P%, didn't say write the percent at the decimal, right? So 90 is 225,000. So quite more expensive for that last 40% than the first 50%. If you look at it, 200,000 for the last 40. According to this model, is it possible to supply to 100%? Looking right up top, the top little part you can see over 100 minus P. The answer would be no, because the 100 is going to be a vertical asymptote. We'll say P equals 100, even though my graph was that, right? It's going to be a vertical asymptote based on the equation. Moving on. And we'll just have a handful more of these find the vertical and horizontal asymptotes, as well as the whole. So again, if you're getting these, you can go ahead, try it on your own, and then check your answer. So denominator equal to 0, opposite of x plus 2 is minus 2. And then checking out 3 over x, we're getting y equals 0. Now, the purpose of going over this so much is this is going to be a small part of the large process of graphing rational function. So they're introducing each piece one at a time so that when we graph this, it's not going to be a terribly long process for each step. Next, x squared over x squared minus x minus 6. Again, set denominator equal to 0 by factoring. I get x minus 3, x plus 2. Set that equal to 0, and I get vertical asymptote is the opposite of minus 3 is plus 3. Opposite of plus 2 is minus 2. There are my two asymptotes. My horizontal asymptote is x squared over x squared. Simplifies to equal 1, so y equals 1. I will only write the holes in there when it is applicable to that problem, by the way. So next one, x squared plus 2 equals 0. That's not going to happen, right? X squared equals minus 2. We're going to have an imaginary number here, so that's not going to happen. So there's going to be none. So vertical asymptote, none. Horizontal asymptote is 6 over x squared. Denominator is going to win that one per se, so then y equals 0. Next one. 6x plus 2 over x squared plus 5x minus 6. Factoring, I get x minus 6, x plus 1. Sorry, plus 6 minus 1. Flip them around. Right? And then set each piece equal to 0, and we get x cannot equal minus 6 for here and plus 1 for here. Horizontal asymptote, comparing 6x to x squared. Right? One of the x's fall off, but 6 over x. Denominator is still going to win, and we get y equals 0. Next, x squared plus 2 over x minus 1. Okay, denominator not equal to 0. Pretty straightforward. Numerator, x squared over x. That would have to simplify something like that. So numerator wins. There's going to be none for horizontal asymptote or null, right? And that's all for that one. Next, 2x plus 3 over x minus 1. Denominator cannot equal 0. Add 1 to both sides. So x equals 1 is our VA. Horizontal asymptote is the 2x versus the x. X's cancel each other, and we get 2, or y equals 2. Couple more left. 2x minus 4 over x squared plus 2x plus 1. The bottom factors to x plus 1 times x plus 1. Numerator to stay the same, cannot equal 0. We get vertical asymptote at x equals minus 1. They're both the same. I don't need a repeat or say multiplicity. And then we got horizontal asymptote of 2x over x squared. Going to give you 2 over x, which is going to lead us to y equals 0. And this has to do with n behavior, right? So the x squared over x squared to finish this up does not equal 0. That one's not factorable, and so we're going to have none. Okay. for our denominator. You could plug it into quadratic formula and you'll realize they're both going to be imaginary numbers. So none for that one. And then we're looking at 3x squared over x squared. Gives us y equals 3 for our horizontal asymptote to wrap up the lesson. If you have any questions, please let me know. And the homework is as assigned.